All right. So we are very happy today to have in the online Horowitz seminar, the second meeting, our very own Matan Seidel, who will tell us about random walks on circle packings. First time with the Zoom system. I hope it goes well. Let's hear Matan.
Okay, so hello everyone. Can you see me and hear me?
Yes, I can see you. And
good.
write in the chat or can indicate with their microphones.
Okay, good. So I'm gonna start now. So my name is Matan, as Ron said. Thank you for having me in the talk here. It's very nice to be here, and thank you all for coming. It's not obvious in this time. I'm now a student of Doron Puder at Tel Aviv University, but I'm going to talk to you about my master's project, which I did under the supervision of Ori Gurel-Gurevich, who is also here in the audience. Ori, you can say hello if you want. Two more things that I want to say is that I tend to speak very fast. I can't really control it, but I can repeat the same things fast a few times. So if I say something which is unclear, then please do tell me, okay? Or if I have audio problems, tell me also. I want you to understand. Okay, so the plan for today is to talk about random walks on circle packings. I'm going to start by giving a bit of background on circle packings. Then I'm going to give some connections to random walk through the He-Schramm Theorem. And then I hopefully will get to state our result and show some parts of the proof. Okay? And this is, I want to introduce you to Joanna Walker. She's going to walk randomly on circles with us today. Okay, so let's get started. Maybe one thing before, the beginning of the talk is going to be about circle packings, but it's actually a talk about random walks. So I'm gonna, to remind you of this, I will put Joanna in the background so you can all enjoy her in the meantime. Okay, so let's start. Okay. So circle packings come from the following natural question. We want to know if there is a canonical way of drawing a planar graph. So most of you probably know that a graph is called planar if we can map its vertices to distinct points in the plane, and we can map its edges to non-intersecting curves, or curves that don't intersect maybe at their endpoints. But there are many ways to draw a given graph, and we want to know if there's a canonical way to do this. So one possible answer for this is circle packings. And a circle packing is just some collection of circles in the plane that have disjoint interiors. And given such a circle packing, such a collection of circles in the plane, we can define its tangency graph to be the graph which is obtained by using the circles as vertices and connecting tangent circles by an edge. So we have one example here, which is the triangle graph. And we can circle pack it as this following configuration of three mutually tangent circles. So when I say we can circle pack it, I mean that the tangency graph of this circle packing is isomorphic to this graph. And here I have the complete graph on 4 vertices. And I want to ask you if you think, how can you circle pack this graph? So this is a question, and maybe you see this, and if not, a possible answer for this is to add a small circle here. I'm not very good at drawing circles, but you can add a 4th circle here, and it will be the complete graph on 4 vertices. And if you want to know more about the radius of this circle, then I suggest to you to read about Descartes' theorem, which tells you this. It's a very nice theorem, so this is homework for later. Okay, so I want to give you maybe a more complicated example, and it's this example. What I want to emphasize, you have a graph here and a circle packing of it. And what I want to emphasize in this is that when you have a circle packing of a graph, it induces a drawing for the graph in the plane. And the drawing is simply by taking the vertices to be the centers of circles and connecting tangent circles by a straight line, okay? So this shows us that if we hope to circle pack a graph, it has to be planar because we get a planar drawing for it. But one natural question is, can we pack any finite planar graph? And the answer is yes, and this is the famous circle packing theorem. So it was first proven by Koebe in 1936 and rediscovered by Thurston and finished following the work of Andreev later. So it has many, many proofs and many versions. And it tells us 2 things. The first part is a part of existence, which basically says that every finite planar graph can be circle packed, or is the tangency graph of a circle packing. So this may seem a bit surprising to you, or maybe not. I don't know how good your intuition is, but when you think about a very complicated planar graph, it's not obvious to see how it can be circle packed. And the second part is a part of uniqueness, which explained why I said that it's a canonical way to draw a planar graph. And the uniqueness part says that if the graph is a triangulation, meaning that all of the faces are triangles, and I include the outer face, it needs to also be a triangle, then this circle packing that represents it is unique up to Mobius transformations and reflections in the plane. Okay, so Mobius transformations and reflections map circles to circles, and they map tangent circles to tangent circles, so we cannot hope for anything better than this uniqueness. But this theorem actually tells us that this is all the degrees of freedom that we have. And a corollary from this theorem is the Farey-Wagner theorem, also proven in 36, which is that every finite planar graph can be drawn in the plane in straight lines, okay? And maybe if I go back to the previous image, you can see that here it's not a triangulation. Both the outer face and this face are not triangles. And you can see, for example, that you have a degree of freedom of, I can take this circle and make it bigger while maintaining the tangency pattern and leaving all of the rest fixed. And you probably know that this will not correspond to a Mobius transformation because I'm leaving many points. Okay. So yeah. Questions about this so far?
Why is the property of a graph being a triangulation independent of the way that it's being embedded into the plane?
Yes, so this is a good question, and the answer is yes, because you can think about why triangulations, finite triangulations are maximal planar graphs. So they're actually graphs that are maximal in the sense that if you add another edge to them, they will become non-planar. Okay, so I hope this answers your question. Okay, so we can ask the same question about infinite graphs, and or maybe before this, I will give some motivation. So circle packings have many applications about a lot of different things. So both combinatoric, so this is what we talked about now, but also very surprising different connections to fields of mathematics, probability, which I'm going to talk about later, but also complex analysis. So here's an example. I'm not going to go into this in detail, but a theorem that was conjectured by Thurston in 85 and proven by Rodin and Sullivan in 87 is that if we have a omega, which is a bounded, simply connected domain, this, for example, then we can use circle packings to approximate the or a Riemann map from it to the unit disk. So you know that the Riemann mapping theorem tells us there is a biholomorphic map which maps omega onto the unit disk, and this theorem tells us that we can approximate it with circle packings, meaning that I can, or maybe this I'll say a bit more about it, and this is that. If I fill this with a triangular lattice, which is what you see here, and I take parts of this graph that are contained inside omega, and then I repack it in such a way inside, this is the same graph packed twice in two different ways, but I pack it now inside the unit disk, I get this two circles, which is the circle in the old graph and the circle in the new graph, and this will approximate in some way, as the radius of these circles goes to 0, this will approximate a Riemann map. And one intuition why this would work is the following. If you think about a Riemann map, it's a biholomorphic map, meaning that it's complex differentiable and it has a non-zero derivative, among other things. But this tells you that if you look very close to a point, then what you will get is that the function only multiplies by a complex number, or approximately multiplies by a complex number, which is a dilation and a rotation. So if you take a circle that is very small or very close to a point, then after applying this function, it will be maybe rotated and maybe dilated, but it will still be a circle. So this gives you some hope that you can approximate biholomorphic maps or conformal maps using circle packings. And this proof says that it's actually true. And maybe if I have time, I'll give more details about this in the end, but I probably won't have enough time. Okay, so one other reason that I talked about this is that in their proof of this, they proved a lemma called the ring lemma, which will be important to us. So the configuration I have here is that I have the unit circle U, and it's surrounded by the other circles forming a chain externally tangent to it. So the ring lemma tells us that I have some R that is only dependent on D, such that if this is the case, if the unit circle is surrounded by D circles, then all of the radii have to be larger than R, okay? Basically saying that if the neighboring circles cannot be too small under the case of only D degree, okay? So this will be important to us when we talk about graphs that have bounded degree versus unbounded degree. So graphs that have bounded degree will also have the property when they're circle packed that neighboring circles are comparable in size in the radii. Okay, so okay, questions about this so far? Okay, so let's move on.
You say graphs, but you mean triangulations, right?
Yeah. I'm going to talk about triangulations from now on. Yes, thank you.
Okay.
Okay, so infinite planar graphs. So when we move on to this case, the theory of finite planar graphs and circle packings was extended in the 90s in a sequence of articles by, among other people, He-Schramm. So I want to talk about what they proved. And when we move to infinite graphs, we need to be a bit careful. We're going to assume about all of our graphs that they're connected. They're going to be triangulations, and they're going to be locally finite, which means that every vertex has a finite amount of neighbors. And when we have such an infinite planar triangulation, I'm also going to assume that they have no outer face. Okay, so when I'm given an infinite planar triangulation, we can ask if it can be circle packed, and if so, is the circle packing unique, and in what way if so? So this is the same question as asking what part of the circle packing theorem extends to the infinite case. And the claim is that every infinite planar triangulation can be circle packed. And the sketch of the proof is as follows. So the circle packing theorem tells us that we can circle pack finite portions of the graph. So what we can do is, it's not very hard to prove, we can exhaust the graph using finite subgraphs, growing finite subgraphs. And we're going to circle pack them and normalize correctly. And when I say normalize correctly, I mean that we're going to choose some special vertex and make sure that it always maps to the unit circle. Okay? And we can do this by applying Mobius transformations. And after we did this, then we can see that, for example, if we take a neighboring circle of it, then it will be always, because of the ring lemma, for example, a neighboring vertex will always be contained, its circle will be contained in some bounded domain in the plane. So we can take a subsequence in which the neighboring circle's center converges, and the radius also converges. And then we can take a subsequence for the next circle, etc., 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 and then take a diagonal subsequence. And then we will get something that we need to show that is circle packing of the graph we started with. And I'm not going to bore you with the details, but this is the idea. Okay, but the question of uniqueness is a bit more complicated. And I think a picture is worth 1,000 words or something. So you can see here two embeddings as circle packings, two circle packings of the same graph. It's the 7 regular hyperbolic tessellation. And once we've, on the left, we've circle packed it inside the unit disk. And on the right, we've circle packed it inside the square. So you can see that the uniqueness statement of the circle packing theorem of the finite case no longer extends to the infinite case, because we cannot find Mobius transformations or reflections in the plane that will map this circle to the square. But you don't need to despair, because there are forms of rigidity of circle packings for the infinite case, and I'm not going to talk about all of them, but I want to mention one which is relevant to my result, or our results. So we need it's the He-Schramm theorem, and we need a few more definitions for it. So if I have a circle packed infinite triangulation, I'm going to define its carrier omega. It's going to be a subset of R2, which is the union of the induced drawing's triangular faces. So the drawing is a triangulation, so I'm going to get triangular faces, and I'm going to take the when I talk about faces, I'm talking about the closed faces, including the edges, and I'm going to take the union over all of these closed faces. In general, it's going to be some domain in the plane, and I'm going to call this domain the carrier, okay? And just to make sure you're with me, so what is the carrier of this circle packing? If someone can volunteer. So I take the union over all of these triangles, which are the faces of the graph. Anyone?
Get to the circle without the boundary.
Yes, exactly. Thank you. So it's the open disk, and if I take the carrier here, it's going to be the open square. Okay, so this is the carrier of circle packed infinite triangulation. And one more definition that we need is that a graph is called one-ended if by deleting any finite set of vertices, I am left with a graph that has exactly one infinite component. Okay, there may be many finite components, but only one infinite component. Okay, so An example for a one-ended graph is z squared, or the square lattice, because no matter how many finite amount of vertices I remove, I'm always left with one external infinite component. And z, as opposed to this, z, or the line graph, is not one-ended, because if I take out a single vertex, then I am left with two infinite components, okay? So now we can state the He-Schramm theorem. They proved it in 95, so let G be a one-ended infinite triangulation, then exactly one of the two following holds. So the first option is that G can be circle-packed with the entire plane as carrier, and the second option is that G can be circle-packed with the open unit disk as carrier. And furthermore, if G has bounded degrees, then the first case is if and only if the simple random walk on G is recurrent, and the second case is if and only if the simple random walk on G is transient. And I will remind you that we say that a simple random walk is recurrent if our random walker Joanna returns to the initial vertex infinitely often, almost surely, okay? And this theorem is quite remarkable in the sense that, okay, in a few senses, I'm gonna say maybe a few more words about it. And the first thing is that it gives a correlation between something that is geometric, which is the ways in which we can circle pack our graph. And the second is the simple random walk on it, which is something combinatorial or probabilistic. So this is something really exciting. And the second thing is that you can think of this theorem as something analogous to the uniformization theorem. So we have two cases. The first case, which we call the parabolic case, is the case in which our graph can be circle-packed with the entire plane as carrier. And the second case is the hyperbolic case, which is when we can circle-pack the unit disk as carrier, okay? And we have two examples here for the two cases. So the first case, we have an example of the triangular lattice, which I've drawn part of it here. So this triangular lattice takes up the entire plane as carrier, and it's, the simple random walk on it is recurrent because it's very much like this. We have the picture from before, the 7 regular hyperbolic tessellation. So the simple random walk on it is transient. You can see that it contains, for example, a 3 regular tree, and it takes up the entire unit disk as carrier. Okay, so yeah. Questions about this, or maybe I'll show a demonstration before. So we have Joanna here. She's going to random walk for us and show the two cases. Okay. So what I wanted to show here is that in the left side, she goes back to the initial circle she started from. And on the right side, she is going to be transient and get smaller in the process. Okay. Okay, questions?
Maybe you can show the animation again?
Yes, yes. Show continuously. I can send it to you later if you want it as a background or something. Okay. Okay, so.
A quick question?
Yes.
How badly do things screw up if we remove the bounded degree assumption?
Oh, okay, great question, because it leads me to the next slide. So we have two assumptions here. The first assumption is one-endedness, and the second assumption is the assumption of bounded degrees. So why do we need these assumptions? And I'm going to talk about the one-ended assumption first. Removing, without the one-endedness, the resulting carrier will have holes, so it's not going to be simply connected. We need to talk about a broader family. We cannot hope in this case that we will have something that can be circle-packed either in the plane or in the unit disk, because both are simply connected. And Ori Gurel-Gurevich, Asaf Nachmias, and Juan Soto in 2017 extended the case to this without the theorem, without the one-endedness assumption. And we need a broader family of domains for it, and let's define parabolicity of a domain. So we're going to call a domain omega in R2 parabolic if for every point x in the domain, and for every open set u in the domain, if I start Brownian motion at x, and I kill it upon hitting the boundary of omega, then this Brownian motion will hit u with probability 1. Otherwise, I'm going to call it hyperbolic. So parabolicity of a domain is going to be some way of saying that the boundary is small. And an example of a parabolic domain is the entire plane, because the boundary is the empty set, And if and Brownian motion is recurrent, so it will hit any open set with probability 1. But also you can notice that if I remove a single point, then it's still going to be parabolic because Brownian motion misses points. And also if I remove any finite number of points, it's going to be parabolic. And an example of a hyperbolic domain is any bounded domain, for example. Okay, so the theorem that Ori Gurel-Gurevich, Asaf Nachmias, and Juan Soto proved in 2017 is that the dichotomy still holds if we remove the one-endedness assumption. And the statement is follows. Let G be a planar infinite triangulation with bounded degrees, then G is recurrent, or the simple random walk on G is recurrent if and only if some circular packing of G has parabolic carrier, and this is if and only if any circular packing of G has parabolic carrier. Okay? And maybe I'll give some motivation. Why did they think that such a theorem would be true? And the answer is that both recurrence and parabolicity have equivalent criterions that look very similar to each other. They're like the continuous and discrete analog of each other. Okay, so let's give them. So here is an equivalent condition for parabolicity. A domain omega is parabolic if and only if for every k compact in the domain and every epsilon larger than 0, there exists a Lipschitz function that takes values between 0 and 1. It's compactly supported in omega. It takes the value 1 on k and such that it has a small quantity like this. This is called the Dirichlet energy of the function. And it's the area integral of the norm squared of the gradient of phi. So we require this to be smaller than epsilon. And the image you should have in mind is the picture on the left here. So we have some function phi that starts out as 1 on the compact set k. It goes down to 0 on some compact set, compact support, and it does so very slowly. Slowly in the sense that if we take the area integral over its gradient, the strength of its gradient squared, then we will get something small, or we can find phi that gets this value to be as small as we want, okay? And here is an equivalent condition for recurrence, and it's the following. Let G be a graph and fix some vertex rho in V, then G is going to be recurrent if and only if, for every epsilon larger than 0, there exists a finitely supported function f on the vertices, with f takes the value 1 on rho, and such that this quantity is small, and the quantity is just summing over all of the edges in the graph of the difference of the value of f squared. Okay, so we can say that f starts out as 1 on rho, it goes down to 0 on a finite set of vertices, it has a finite support, and it does so slowly in the sense that if we take the sum of the differences squared over all of the edges, that's something small. Okay? Questions about this? Okay. So I'll continue. Okay, so the bounded degree assumption, this is to the question I was asked earlier. So the bounded degree assumption is a bit harder to remove because if we remove it, the He-Schramm theorem will fail or might fail, at least one direction of it. Actually, they need it only for one of the directions. So an example we can give is the following. So we take part of the triangular lattice, I've drawn part of it, and we add circles to the circle packing. So I'm going to add 1 circle here, I'm going to add 2 circles here, I'm going to add 4 circles here, 8 circles here, etc. And you can think that this has a symmetry vertically. So all along here I have 1 additional circle, all along here I have 2 additional circles. And what I claim is that this, the simple random walk on this graph is going to be transient. And the reason is that whenever Joanna visits one of the circles here, she sees approximately twice as many circles to the right than as many circles to the left. So this is going to give a bias to her random walk, which is going to make the random walk transient. She will have a drift. And here you can see Joanna trying to walk randomly, but she's experiencing a drift to the right, okay? But what you should notice is that the carrier of this circle packing has stayed the same, right? The carrier is still the entire plane. So this is an example of a circle packing that has a carrier that is the entire plane, but the simple random walk is transient, okay? And you can, but we shouldn't despair. So an idea for how to make a version of the theorem still work is to replace the simple random walk with a weighted random walk. Okay, so this is what I'm going to talk about next. And you can recognize these ways from the talk that Asaf gave in the Horowitz seminar. So the idea is to use a weighted random walk. And by weighted random walk, what I mean is that a random walker, Joanna, will choose an edge with a probability proportional to its weight. So we place weights on the edges. It's going to be a specific set of weights that I'm going to define soon. And whenever she visits a vertex, she's going to look around her and she's going to choose her next edge proportional to the weights that she sees. So the probability of her taking an edge is going to be the weight of the edge divided by the sum of weights around her, okay, around the vertex she's at now. And these edge weights are geometric weights arising from the circle packing that are very natural. And they were introduced by Duffin in '68 in the context of the discrete complex analysis, and reintroduced here in this context by Dubeyko in '95. And the reason we want to use this random walk, this weighted random walk, is that it has really nice properties. So the first property is that if we take the sequence of centers that a random walker visits along the random walk, the points in R2 that are the centers of circles visited, it's going to be a martingale. Okay, so this is, Dubeyko proved this in '95. The second property that I'm going to talk about is that the weights are bounded from above always by a universal constant, or so this constant is maybe very universal, it's just one. And under the bounded degree assumption, we have the ring lemma, which will tell us that neighboring circles are comparable in size, and this will imply that the weights are also bounded from below by a constant. And these two things together, the bound from above and from below by a constant, using Rayleigh monotonicity, which is a theorem in electric networks, this will tell us that it doesn't matter if we're looking at the simple random walk or the weighted random walk in terms of recurrence or transience, because we will have that either both are recurrent or both are transient. So what we hope is that by replacing the simple random walk with the weighted random walk in the He-Schramm theorem, we will get something that is actually a valid statement, okay? Without the bounded degree assumption. And the theorem that we proved is one direction of this, which says that if we take a circle packed infinite triangulation with parabolic carrier, then the weighted random walk on it is going to be recurrent. So if I go back to this slide, so Joanna, when she was walking here, making the simple random walk, then she was transient, but if she's going to make the weighted random walk, she's actually going to be recurrent, which is what we want, okay? Questions about this? No? You can ask also in the chat, I'm looking at it. So if you want to ask something, feel free. Okay, so I'm going to continue. So let's give a definition of the weights. So I've drawn here a circle packed infinite triangulation in black. And what I want you to notice is that when we have a circle packed infinite triangulation, it induces also a circle packing for the dual graph. So the dual graph is the graph that has the faces as vertices. It replaces the faces and vertices. So the circle packing that I'm going to take for the dual graph is just the incircles of every face. So here, for example, I have the edge E, and it has two faces incident to it. And I'm going to draw the incircles of these two, of these two faces. And what you should notice is that I'm not going to prove this, but the point of tangency of these two circles are going to be tangent to each other. Their point of tangency is going to be the same as the point of tangency of the primal circles, and it's going to be tangent orthogonally. So the purple circles and the black circles are orthogonal to each other. So we get, we get a dual edge here that is E dual. And once we notice this, we can define the weight of the edge E to be just the length ratio, the length of E dual divided by the length of E, okay? And the theorem that Dubeyko proved in '95 is that if we take the sequence of centers of circles traversed in the weighted random walk, it's a martingale. So this is the martingale property, and we're going to get a lot of profit from it for free. So let's prove this because it has a really nice proof. So the proof is as follows. I've drawn here a single circle V, and I've drawn its neighbors, which are U1, U2, U3 through UN. I've drawn the edges, E1, E2, until En, and the dual edges F1, F2, etc. until Fn. And I want you to also notice that if we take all of the dual edges for the edges incident to V, then what I get is a closed polygon bounding the circle of V. Okay, so this is something to notice for later also. Okay, so what we want to show is that the weighted random walk is a martingale, and we already know it's a random walk, so it's a Markov chain. So all we need to prove is that the expected change across one step is 0. So let's start our weighted random walk as V. And what we want to prove is that the sum over I equals 1 to n of the probability of moving to a vertex ui times the vector of change ei is 0. And notice that this is not exactly the probability. This is the weight from v to ui. I was supposed to divide this by the sum of weights around v, but to prove that it's 0, I can multiply out by the sum of weights. So this is actually what I need to prove. And indeed, I can take r to be a 90-degree clockwise rotation. And what you can notice is that if I take some edge, let's say E2, and I rotate it by 90 degrees, I get something that is parallel to F2, okay? So when I apply R to this vector that I want to show that it's 0, then I can put R inside the summation and then plug in the definition for the weight, which is the length of Fi divided by the length of Ei. And then I can see that REI is parallel to Fi. And if I divide it by the length of Ei and multiply it by the length of Fi, I just get Fi. And summing up from I equals 1 to n, the dual edges is just tracing out a closed polygon, which will be 0. Okay, so questions about this? Okay.
Could you say again the second equality?
Yes, so here to here. Yes, great, thank you. So when I apply R is a 90-degree clockwise rotation, anti-clockwise, sorry. So if I take E1, for example, and I apply R to it, then what I get is something that is parallel to F1, but is in the length of E1. And if I divide it by the length of E1 and I multiply it by the length of F1, I just get F1 as a vector. Okay?
I see, thanks.
So, thank you. And when I sum up all of these vectors, it's summing up along a closed polygon, so this will give me 0. Okay. So this shows that we have a nice martingale property. And let's show how we can use this. And an example is a special case of the converse. So let's assume I have a bound carrier for my circle tracking. And when I know that the carrier is bounded, it's also a hyperbolic domain. And I want to show that the weighted random walk is transient. Okay. So here's the proposition. The weighted random walk xn on a circle packed infinite triangulation with a bounded carrier is transient. So let's prove this. So I fix 2 vertices in the graph, rho and rho prime. And I look at the weighted random walk xn. It's a martingale, we proved this before, and it's also a bounded martingale because it's contained inside bounded omega. And bounded martingales converge almost surely, so we have some random variable x such that xn converges almost surely to x. Now, suppose towards contradiction that we have recurrence. So recurrence means that our random walker Joanna will return to every vertex infinitely often, almost surely. So in particular, almost surely we will have that xn is equal to rho. But xn is almost surely also a convergent sequence that converges to x. So x must be also equal also surely to rho. Okay? A convergent sequence that is almost, that has infinitely often rho has to be with a limit rho, okay? But this is also true for rho prime. So we almost surely have that x is equal to rho prime. And this is a contradiction because the same random variable cannot be equal to both rho and rho prime almost surely. Okay? Questions about this? No? Okay. Okay, so let's continue. So let's restate our theorem. So the theorem that we want to prove is that the weighted random walk on a circle packed infinite triangulation CV is with parabolic carrier omega is recurrent. So now I have a carrier that is parabolic, and I want to prove that the weighted random walk is recurrent on it. So let's give a sketch of the proof, and then I will focus on some point of the proof. So we want to use the equivalent criterion for recurrence, or the weighted version of it. So I want to find some function f on the vertices that is finitely supported, that has the value 1 over the vertex rho, and that has a small discrete Dirichlet energy, which means that if I take the sum over all edges of the graph of the weight, this is the weighted version, so I need to take the weight of the edge as well, and multiply by the difference of the value of f across the edge squared. I will take this sum. I want it to be as small as I need, okay? And how will I do this? So I know that my domain is parabolic. This, from the equivalent criterion for parabolicity, I know that I can get some nice function phi on the domain, phi from the domain to 0, 1. and I can demand a few things on phi. So the first thing I can demand on it is that for the polygon of rho, I fix some vertex rho in the graph. I can demand on it to be 1, and I can take f to be the restriction of the value of the phi function to the vertices. Okay, this is how I have this function defined continuously on omega, and I will take the vertex function to be just the restriction on the vertices. So I can demand on phi that it will be equal to 1 on k, and this will imply that f will be equal to 1 on rho. Phi is going to be compactly supported, so this will imply that f is finitely supported. This implication may not be obvious to you, but it's technical and not very interesting. You can ask me about it later. And the third thing we know about phi is that it has a small Dirichlet energy. So the area integral over the norm squared of the gradient of phi is small. Okay, so this is the things I know about phi. And the only thing I need to finish my proof is to bound the energy of f. Okay, this quantity. So how do I do this? Questions about this part. This is very similar to what Ori Gurel-Gurevich and Asaf Nachmes and Juan Soto, they did in their proof of, yeah. Questions? No? Okay, so let's move on. And how do we bound the discrete sum? So we have a discrete sum, and the sum is over differences in the value of f. We want to bound it with some two-dimensional integral. So we need to convert it to an integral in some way, and we are going to convert it to some weird two-dimensional integral on polygons. And the way to do it, or how we did it, is the first part is using the fundamental theorem of calculus. So you have a difference in the value of a function. You can convert it to be an integral over the gradient along a curve connecting these 2 points. And we can do these things along many, many different curves and then average out. This will give us a second integral. And we also use some Cauchy-Schwarzes and some estimates on Euclidean geometry. This is this part. And then we need to bound this two-dimensional integral to the integral that we get. On polygons, we need to bound it with the quantity that we know that is small, which is the Dirichlet energy of phi. So we're going to split into 2 cases. For good angled polygons, which is, I'm not going to define this precisely, but you can think about good polygons to be polygons that have large angles, or in other words, that are very, very close to the circle that they bound. Okay, so this is an example of a good polygon. So for good angled polygons, we can actually bound this integral with a continuous Dirichlet energy using some harmonic analysis. And why do we have harmonic analysis here? So the reason is that we can also actually assume that our function phi is also harmonic, because harmonic functions are minimizers of this quantity called the Dirichlet energy, so we can assume it on the interior of polygons to be harmonic. Okay, I don't want to go into the details of this, but this will give us access to harmonic analysis, and we can use a bit of Harnack inequality and stuff like that to bound it for good angled polygons. And for bad angled polygons, which is this case, so what you see here is that you have this tiny circle that is stuck between 2 very, very large circles. So what happens here is that if you look at the polygon bounding it in the dual graph, then the polygon is going to have this very, very acute angle. So this is going to be very bad. This polygon doesn't look at all like the circle that it's bounded in. And if I have this circle being much pushed further inside, then this is going to be worse and worse. So for this type of polygon, we have a different solution, which is to just fix the graph or replace it with a different graph to get a bound in another way. And the keywords for this part are martingales, Markov chains, coupling, and electric networks. And I want to focus on this part. Yeah, so this is what I want to focus about. Questions about the sketch of the proof? Okay, so I'll move on. Okay, so now I'm going to take a few steps back, and that is going to look like I'm not saying anything, but it is actually saying something, and I need to be very, very rigorous for you to understand that it's actually saying something, I think. So we're going to do things very, very rigorously and slowly. So I'm going to define a network to be a pair VC, where V is my state space or vertex space, and C are just some non-negative weights that I put on pairs of vertices. I'm allowing the weight of 0, such that they have the following properties. I want them to be symmetric, so the weight of xy is going to be the weight of yx for every pair of vertices. I want it to be normalizable. So if I take pi x to be the sum of all the vertices around x of the weight, then I want this to be smaller than infinity and to be finite for every vertex x in V. and I want it to be connected. So I can take a graph from such a network by considering connecting xy by an edge if their weight is positive. And when I take this graph, I want this graph to be connected, okay? So when I have such a network, I can think about the weighted random walk on it, okay? This is with the weights from the network, okay? And a definition that I want to use is that when I have a Markov chain on a state space V, I'm going to say that it's represented by the network VC if its transition matrix P satisfies that the probability of transitioning from X to Y is the weight of XY divided by the sum of weights around X. So this is another way of saying that the Markov chain is actually a weighted random walk on this network, okay? And two things I want you to notice is that the weights are not unique. If I multiply all of my weights by some positive constant, then it will represent, it's going to be another network representing the same Markov chain. And another thing that I want to say is that in the language of Markov chains, this symmetric, normalizable, and connected properties are all saying that my network my Markov chain is irreducible and reversible. Okay, so this, but maybe you shouldn't think about this. Okay, so I want to define two things that I can do on a Markov chain. Okay, so let's say I have a Markov chain Xn on a state space V. So the first thing that I want to define is what censoring it is. So let's say I have a finite proper subset W. I consider V prime to be the remaining vertices. And I say that the chain censored to V prime is the process that is obtained by deleting appearances of W from the random sequence that I have. And the chain, when I delete repetitions, this is a second operation, it's just going to be the process that is obtained by deleting adjacent appearances of the same state from the random sequence. So I have an example here. So I have a state space V with three vertices, W, V, and U, and I take W to be just the singleton W. So let's say I have some sequence that turned out randomly to, which is V, W, V, U, W, etc. And if I censor it to not have W, then I get this random sequence, which is V, V, U. And if I do another operation of deleting repetitions, then I get VU, etc. Because you can see that when I delete a W, I have this repetition appearing suddenly. Okay, is this clear what I'm doing? If this is unclear, ask questions. Okay, so silence means I can move on or something. Okay, so so we have this operation on the Markov chains, and I want to see how it reflects in the language of the network that is representing it. So let's say that I have VC, which is a network, and Xn is a Markov chain that is represented by VC. So the first operation, if I have W, which is a singleton, and I take V prime to be V minus W, then the chain censored to V prime is represented by V prime C prime, whereas C prime is almost the same as C, except that I need to add this correction factor. So I need to change the weights. If I could get from X to Y through W, I need to add this factor here of the transitioning from X to Y through W, okay? And the repetition deleted, or maybe I would say one more thing. In particular, what I want you to take from this is not exactly this formula, which is not very important, but I wanted you to take that this new Markov chain that we get is actually irreducible and reversible, which might not be obvious. I don't know, maybe depending on your intuition. Okay, the second thing that I want to say is that the repetition deleted chain is represented by VC prime, where the new weights are just the old weights, except that I'm deleting loops. So C prime xy is the same as CXY if X is different from Y, and it's going to be 0 if X is Y. And I've given here an example. So if I have A, W, and Z, this is my state space, and I have an edge here with weight C1 and an edge here with weight C2. So if I censor out W, I get this network. So notice that it adds loops because I can get to A back from A back to A through W. And if I delete repetitions, then the network I get is just the loops deleted. And some of you may recognize this expression here, which is just the connection in series of conductors. So this is lo bichdi. I don't know how to say lo bichdi in English. This has a reason. Yes, okay. So yeah. Questions about this? Feel free to stop me if you have questions.
In this drawing, I didn't quite understand. Is W connected only to A and Z?
Yes, yes.
Okay. Now I understand. Okay.
Yes, thank you. So W is connected only to A and Z, and then I delete its appearances in the Markov chain, and in the network, this reflects by making it disappear and adding the loops here, okay?
And it will be more complicated if W has more neighbors and you want
Yes,
to
yes, exactly. And we can do this repeatedly for many vertices one after the other. Okay, so let's continue and state the lemma that I wanted to state. So I have two configurations here, one on the left and one on the right. And the configuration is as follows. I've taken three circles in the graph that form a triangle. So I have X, Y, and Z, which are mutually tangent to each other, okay? And I'm choosing such a triangle in the graph such that if I take W, capital W, to be the set of circles that are contained in this triangle, then this set is going to be finite. So I have a finite amount of circles that are stuck inside some mutually tangent triple in the graph. Okay, so this is the configuration that I have on the left. And on the right, I've performed the operation of just like removing the circles from my infinite circle packing, okay? You can notice a few things. The first thing I want you to notice is that the new configuration is also a circle packed triangulation because I've chosen XYZ to be a triangle. So this is still a triangulation and a circle packed triangulation. The thing I want to notice is that when I do this operation, the weights on the weighted random walk are changing. And this is because if I take this dual edge, it's going to become longer. Right? When I delete the vertices of W, the dual edge here is going to become longer. So this will change, for example, the weight of the edge XY. Okay? And the lemma is going to tell us the following. It's going to give us a coupling between the random walk, the weighted random walk on this configuration and the weighted random walk on this configuration. And the weighted random walk is going to be by taking this random walk, deleting the appearances of W, censoring it to V minus W, and then deleting repetitions. This will actually give us a weighted random walk on this right side. So let's read the statement of the lemma. So let's say I have CV for V in capital V, a circle packed infinite triangulation, and I have CX, CY, and CZ mutually tangent circles, such that the set of vertices W that is contained inside the triangle XYZ is finite. And then I take a xn to be a weighted random walk on CV, V, and V, on the configuration on the left. Then the chain that is obtained by censoring xn to V prime, which is V minus W. And then deleting repetitions is represented by the weights of CV, where V is in V prime. Okay, so is it clear why this lemma is actually stating something? Or do you have questions?
In particular, in the example you gave in the beginning of the triangular lattice with circles added, then you're claiming that after censoring the added circles and deleting repetitions, you just get random walk on the original triangulation.
Yes, exactly. And we're gonna, this is good. Yeah, questions about this? More questions?
Yeah, just so the reason that you're bothering with this repetition deletion, because the repetition deletion doesn't really change recurrence or transience properties, but it's so this equality holds.
Okay.
That's the point there.
So repetition and deletion, if I do it in one place, it's not going to change recurrence or transience, yeah? And if I do it in many places, in general, if I don't have this lemma, I don't know how it connects to transience or recurrence, and I'm going to do this, or maybe I'll just show the next slide, and I think it will answer your question. So how do I use this lemma? And the idea is that I want to insert circles to push bad polygons away. Okay, so let's say I had this. Apparently, bad polygons arise only in this case that I showed you. So it can only arise when I have two really big circles and a small circle that is stuck between them. Okay, so what I can do in this process is I can actually do the lemma but in reverse, and I can insert circles to the graph. So I can make this configuration on the right, and I can insert as many circles as I want. And what you can notice is that the original bad polygon has now become a good polygon, but I have to pay the price, which is that the last circle here will be a very, very bad polygon. But I have the advantage that this is really small, meaning that if I look at the edge connecting, the bad edges connecting this circle to the huge circles around it, then this edge is not only small, the weight on it is not only small because it's this value, this length divided by the huge length. So it's small and controllably small. So if I have infinitely many appearances of this in my circle packing, then I can actually do this process and make such that the sum of all of these bad weights will be not only summable, but with small sum. And then I can use the trivial bounds. So I wanted to bound this expression, which is the weight times the difference in the edge of the value of f squared. And f is bounded between 0 and 1, so I can just use a trivial bound of bounding all of this square thing by 1, and I get just the weight, which is small. Okay? And the lemma, the reason I am stating the lemma is that it will give me that the original network is recurrent if and only if the new network is recurrent because they are coupled, or in other words, they have the same effective resistance to infinity. Okay? Does this answer your question?
Why does CXY become small if you insert more and more of these circles here? Okay,
I'll say this again. So the CXY, the weight here is becoming small because the weight is just this dual length of this purple line divided by the sum of the radii, the distance between the centers of these circles. And if I do this for this bad polygon, or I do this for this bad polygon, then it's going to get much smaller because this length here is going to get, the dual length is going to get as small as I want if I insert more and more circles.
Okay.
Okay, is this clear?
Okay, I'll think more about it. Thanks.
Okay. Okay, so let's prove this lemma. And this is the last thing I will show you.
I would like to add something about what Ron's question. Was it wrong? So I think that in principle, you could also do the same proof by actually adding infinitely many circles there. They will get smaller and smaller and smaller and smaller. But we didn't go this way because it was more technically complicated. I don't think that, and then this part that you're concerned about will completely disappear. Okay, but instead you will have all kind of, concentration point, and I don't know. We didn't go this way, but I think it's possible.
Yeah.
Sure. Maybe I was not quite clear about who is X and who is Y in this CXY. But
yeah, so CXY, I was comparing CXY to be the original bad edge and the new bad edge. So the original bad edge had this length in the denominator, in the Monet. I'm not sure which it is. Yeah, numerator, thank you. And the numerator gets as small as we want by pushing, of the bad polygon gets as small as we want by pushing in more circles. Okay, so let's continue to the proof. And I need some notation, so try to follow because it's really nice. We're my martingale magic happening here. So I'm going to have 3 Markov chains. The first is xn, which is the weighted random walk on the original network. So I'm reminding you, I have the xn is going to be the weighted random walk on when I still have the W circles. And I'm going to denote its weights by C. And I have the chain yn, which is the censored and repetition deleted xn. And I'm going to call this C prime. And I have Zn, which is the weighted random walk on the new configuration after I've deleted the circles from this configuration. And I'm going to call this C double prime. And what I want to show is that C prime is actually equal to C double prime. Okay? And what you can note is that for all the edges that are not in this triangle XY, XZ, YZ, then I'm actually not doing any changes. So C prime UV is going to be equal to CUV, and C double prime UV is going to be equal to CUV. So the reason that C double prime UV is equal to CUV is because we're only changing things locally, which means that dual lengths or lengths are not going to change outside of the triangle XYZ. And the reason that this is happening is because maybe you can think that I'm not doing any changes to the transition probabilities from edges that are not X, Y, and Z. And another way to see this is the proposition that I mentioned earlier. So we are only going to change the weights if I can get from a vertex to another vertex by going through W. And going through W is only something possible for X, Y, and Z. Okay, so I already have this equality for all the edges besides the edges of my triangle. So let's prove it for the triangle, for these edges, and I'm going to prove it two equations that are very similar to each other. So first, we're going to start from the second configuration. So I have X, Y, and Z, and I've deleted the circles of W, and I'm looking at the Zn chain, and I've also drawn U1, U2 through UN, which are all of the other neighbors of X. So I'm going to start the weighted random walk at z null, which is x. And we know that Zn has the martingale property. So this will tell us that the expected change across one step of z is going to be 0. But we can write out this expected change explicitly, and it's just the sum over all of the transition probabilities times the vector of change. So it's the sum from I equals 1 to n of c double prime x ui divided by pi double prime of x times ui minus x. And I need to add also the vectors of change of y and z. Okay? And what you can notice is that I can multiply out by pi double prime x because it's dividing everything here. And I can also remember that this c double prime xui is equal to cxui because these edges are outside of the triangle that I have. Okay, so what I get is this equation, the sum over I equals 1 to n of cxui times ui minus x plus c double prime xy times y minus x plus c double prime xz times z minus x is equal to 0. Questions about this? Okay. So I'll move on, and we're going to do the same thing in spirit, but a bit more complicated. So we're talking about the first configuration now. So I do have the W circles here. It's just one circle, but it could be more, but a finite amount. And I'm going to start a random walk, a weighted random walk on this at x again. So x0 is x. And now what I'm going to do is I'm going to set a stopping time tau. And the stopping time tau is going to be the first time that I leave the set of both W and X. So it's the first time that I leave W and X, and it's going to be actually the first time that I see one of the other neighbors, the first time that I see Y, Z, or one of the U vertices. So formally, tau is going to be the infimum over positive times T, such that XT is not contained in the union of W or X, okay? And Xn also has the martingale property because it's a weighted random walk on a circumflex infinite triangulation. And they can use Dub's optional stopping theorem to get that expected change between the 0 time and tau time is 0. Okay, so this is Dub's optional theorem is the first equality here. And now what you should notice is that x0 is just x, and it's also equal to y0. But also we have that x tau, the first vertex that we see when we leave x and w, is actually going to be y1. It's going to be the first vertex that we see in the chain that is when we delete w and then we delete repetitions of x. Okay, is this observation clear? Or should I repeat it?
Can you repeat it, please?
Yeah, okay, thank you. Okay, so I've set a stopping time tau to be the first time that I leave both x and w in my weighted random walk xn. The stopping time is just when I leave x and w, so it's actually the first time that I reach one of the vertices that is y, u1, u2, un, and or z. One of these vertices, the first time that I see it. And when I stop, when the first vertex that I see, I claim that it's actually going to be the first vertex appearing after x when I delete appearances of w from the random sequence of xn, and then I delete repetitions of x. Okay, so
we don't yet know that that y is even a martingale, right? That we're proving that we're going to prove that y is a martingale, but we don't have that information already.
Yeah, we don't have that information already. Yeah, exactly. Okay, so I can now write explicitly the expected difference between y1 and y0 the same as I did before, except that I have prime instead of double prime, right? It's the sum over I equals I to n of the probability of transitioning times the vector of change, also for all of the ui's, and then for y, and then for z. And I can do the same thing. I can multiply out by pi prime of x, and I can remember that c prime xy is equal to cxy, and I get a very similar equation to what I have before, just with 1 prime instead of double prime. So someone asked why is tau integrable, and maybe I don't want to talk about this, but actually it's you can think about this. It's not yeah. For example, yeah, it's never mind. We can apply Dub's optional stopping theorem. It's I don't want to get into the details. Okay, so what I want to do is that we have two very similar equations, so we can subtract them. And when we subtract them, we get the following equation, that c prime xy minus c double prime xy times y minus x plus c prime xz minus c double prime xz times z minus x is equal to 0. So the whole sum that we had in the beginning of the equation cancels out. And what you can notice now is that y minus x and z minus x are edges of a triangle. And in particular, they are linearly independent. This will tell us that these coefficients have to be 0, okay? And this tells us that this actually finishes the proof, because this shows that C prime xy is equal to C double prime xy, and C prime xz is equal to C double prime xz. And a similar argument for y instead of x will show us the third edge also. Okay, so do you have questions about the coupling lemma? So maybe I will answer the question because, okay, so one way to see that we can apply Dub's optional stopping theorem is that tau is almost surely finite, and the martingale is bounded because we're stopping it only on this portion of the, okay, so this should answer your question, I think. Okay, more questions. Okay, so if no more questions, then thank you. And this is the weighted Joanna doing a weighted random walk on circles.
Very nice, Matan. Let us all clap hands. We might have this in the reactions, by the way. I'm not sure, in the reactions tab of Zoom. We have something at least. Okay, so any other questions to Matan for this very nice talk? All right, there were many questions during the talk. So thank you all very much. Next week, we're going to have Nathaniel Berestiki from the University of Vienna, who will tell us about, I'll send the announcement. I don't have it in front of me at the moment. I hope to see you all there. And I hope also to upload this video to the internet, and I'll send the link. Okay, thank you very much, and see you next week.